Good afternoon, everyone. My name is Suleimenova. I'm a lecturer in the Department of Computer Science at Brunel University, London. Prior to that, I was a research fellow in multi-scale migration prediction within the VVUQ project. And now currently I'm also a research knowledge exchange coordinator for CVA project, where we aim to organize different types of hackathons, seminars, and workshops in the use of VVUQ. So if you're interested in the future events within the VVUQ project, please let me know after my talk. So today's talk, I'll be focusing on the state-of-the-art methods and tools within the VVUQ. To start with, all models are abstractions of the real activity that are based on many different types of approximations. These models are formulated and programmed in a digital computer, which produce different types of simulation results. These simulation results, after analyzed, and they may have fidelity that might be under question. So there's a question for us to ask whether these results that we obtain actually have high fidelity, or they might actually make no sense to us. That's why, to answer these questions, I wanted to draw your attention to the concept developed or framework developed by Society of Computer Simulation. They also raised by modeling, simulation, and simulation, or also known as operations research. They suggested two types of models when you're trying to create a model of real activities, and they based it in the conceptual model. Whereas the second model focused on the computerized model. And while they identified these two types of models, they also tried to investigate the model qualification and why they meant between the reality and conceptual model. The qualification is that it's a determination of adequacy of the conceptual model to provide an acceptable level of agreement for the domain of intended application. Whereas the main focus was to define verification and validation that they wanted to understand that exists within conceptual model when you're trying also to computerize your model and obtain some kind of results. And how they defined verification is that verification deals with the relationship between conceptual model and the computerized model, whereas validation deals with the relationship between the computerized model and the reality. Of course, there are many other definitions that exist that, for example, SME guide provides us. But the important aspect within this is that we should not forget about the uncertainty quantification. When we're trying to understand what is uncertainty, in the most literature, there are two different types of uncertainties that come along. First is the aleatory, meaning that uncertainty due to inherent randomness. What it exactly describes is that it is the natural variability of quantity of interest that you're trying to understand within your model. Whereas the second type of uncertainty, which is the epistemic, it tries to identify uncertainty due to the lack of knowledge. So any type of knowledge, it might have some kind of lack, and it also potentially reducible by acquiring more knowledge. So after defining these two different types of uncertainties, what we can understand is that in the literature by Oberkampf and Roy in 2010, they defined 3 steps that can be applied when you're trying to use models and try to run different types of simulations. And in identifying uncertainty, these 3 steps are, first is when you try to characterize the source of uncertainty. Which kind of uncertainty do I have within my model? Whether it's the first one or second one, or it can be a combination of both. Also, after you identify the type of uncertainty you have within your model or in your input parameters, what you try is to propagate your uncertainty inputs within your uncertain model that actually provides uncertain outputs that actually reflects to the analysis where you're able to achieve by ensemble of cumulative distribution functions, or you can have different types of sensitivity analysis, such as Sobel indices, for example, to achieve the results that you want to obtain. So within the UQ or VVUQ area field, there are different types of tools that can actually help you in understanding how you can identify within your model the uncertainty quantifications. So here, for example, in the table on the right-hand side, you can see that there's a list which are prominent tools that exist. So I'm going to view a number of them, which is Dakota, focusing on optimization in DQ, and also general purpose uncertainty propagation, surrogate modeling, and sensitivity analysis, model calibration. So it provides different types of analysis that you can apply. Whereas UQ Toolkit, it's a set of different components and tools that are available to quantify uncertainty. And it allows you to run surrogate models and then achieve, analyze sensitivity analysis, and then also the additional aspects within the UQ Toolkit. These both tools were developed in the Sandia National Laboratory in the US, whereas UQPy is a uncertainty quantification with Python. It's a package provided by within the Python that you can actually use within your simulations to understand the uncertainty within your model. The key aspects within the UQPy is that it has uncertainty propagation and stochastic processes. It's based on Python language, as I mentioned earlier. Another tool that I want to mention is the UQ Lab. And the UQ Lab, it's a MATLAB-based tool. And if you think about it, there are other tools that are here which are developed in R, Python, MATLAB, or C++, or other languages can be used as well. At the same time, you can operate with these tools within your desktops, which can be Windows operating system, Linux, or Mac. At the same time, you're able to run on the supercomputers. So in relation to the UQ Lab, is that the main purpose or general purpose of it is the uncertainty propagation, surrogate modeling, and sensitivity analysis. So if you think about it, they all have similar aspects that they want to achieve. But today, I want to draw your attention to a different tool, but also focusing on the VVUQ. So the main tool that focuses on UQ analysis is, the EasyVVUQ, and focusing on validation and verification is FabSim3. These two tools were developed or are the components of the VECMA toolkit. VECMA toolkit is a toolkit that was developed within the VECMA project that we worked in the last 3 years. So to give more details about the EasyVVUQ, EasyVVUQ stands for Verification, Validation, and Uncertainty Quantification that aims to make it easy as possible to implement advanced techniques for uncertainty quantification for existing application. So any application user are able to download using PIP, the EasyVVUQ software, and able to run UQ analysis or sensitivity analysis. It primarily focuses on non-intrusive UQ techniques. What it means that you don't have to, when you run your model, you don't need to make the various changes. The main aspect is that you are able to quantify uncertainties and analyze the uncertainties or parameter sensitivities. Here's the basic workflow of the EasyVVUQ. What you have is that you have an input or model parameter description where you provide minimum, maximum values of your parameters within your model. And what happens after within the EasyVVUQ, these input parameters are sampled. When you try to sample, there can be different types of sampling methods that are also included in the EasyVVUQ. I'll describe them in the next slide. And then after sampling, what you're able to is to create an ensemble of simulation where you can run these different types of parameters with different propagated numbers, and you can execute it. After execution, you're able to obtain your results. So you're able to post-process and analyze. And after analyzing, you understand, okay, do I actually, the source of uncertainty defined, did I actually understand whether it was identified? If it was, then you stop your uncertainty quantification analysis. If it wasn't, you go back to sampling and perform the same set of steps again. In relation to EasyVVQ sampler methods, there are, at the moment, we have Monte Carlo, quasi-Monte Carlo, polynomial closed expansion, stochastic collocation, adaptive stochastic collocation sparse grids that Wouter mentioned today. And there are more other methods that are in the plan to be added. All these methods can be used to calculate Sobel sensitivity indices. And as you can see in the graph on the right-hand side is an illustration of how Sobel indices are identified. Again, this graph is very familiar to you as you've seen it in the previous presentation. What you have on the x-axis is the number of simulation days that you have. On the y-axis is the Sobel indices ranging from 0 to 1. And you're able to use EasyVVQ when you obtain your simulation results and visualize your results by seeing all the output results that you have per parameters. You're able to plot the most important or influential parameters within your simulation. And you can also visualize each single parameter, how there's Sobel indices within these parameters. In relation to the enhances workflow, so EasyVVQ is integrated with the rest of Python-specific infrastructure, and it accesses through the wide range of sampling approaches using QSPy. It adapts user existing code via extension of encoder or decoder classes. What do I mean by that is that here you have the sampling, another workflow demonstration of the EasyVVQ here. You have the sampling of your input parameters. We're able to encode within the EasyVVQ the number of parameters that you have and what kind of ranges you want to use. That's stored within the EasyVVQ. After you encode your input parameters, you're able to execute, which is afterwards decoded, meaning that all the output that you achieved are actually stored within the campaign database within the EasyVVQ. And from that campaign database, you're able to take your output and analyze and obtain your results. Understand which input parameter actually influential to your simulation output. In relation to the EasyVVQ, now the main point just I wanted to highlight is that it minimizes boilerplate code requirements, meaning that you don't need to make big adjustments within your application or within EasyVVQ in order to understand or to implement the UQ analysis. So we try to minimize the setup overhead for each application user. Also, it takes care of bookkeeping, meaning that you can create different types of folders within EasyVVQ. It can store results, as well as it collects all the meta info in the database. So one of the things that Wouter was mentioning, when the number of samples with polynomial orders expanded, EasyVVQ has capacity of storing these results as well as to analyze them. EasyVVQ can be executed locally, meaning that in your local machine without installing any additional tools apart from EasyVVQ, you're able to run your executions. You can also integrate EasyVVQ with the supercomputer. So one of the instances, for example, we've used within our project is the Eagle supercomputer in Poznan using the QCG pilot job scheduler. It also integrates with FabSim3, its automation toolkit that I will describe in the coming slides, as well as with the Dask. Another main advantage of using EasyVVQ is that you're able to execute it on cloud HPC using Kubernetes.
Diana, you have 5 minutes more.
Thank you. So in relation to the FabSim3, so FabSim3 is a user-developed oriented automation curation toolkit. So it aims to automate any functionalities or tasks that you like to perform within your application using the FabSim3 toolkit. So it reduces the human effort required to create, modify, repurpose complex computational workflows. It also uses generic pattern code for UQ analysis and the VNV, I'll demonstrate more details about the VNB. So it again, FABSIM3 can be executed locally on supercomputer or in a QCG broker or pilot job schedulers. FABSIM3 is generic in nature. However, the specific plugins are within the FABSIM3 that are focused on your application. So I can give you an example. As I said, I was a research fellow in multi-scale migration prediction, and I have my own plugin within the FABSIM3, which is called FabFlea, which has its own application with the different automated tasks where I'm able to run my UQ analysis, VNB analysis, as well as to perform high number of executions, whether the ensemble runs or the replica runs. These are the examples of the executions. So you have the main command, which is FABSIM3, localhost if you're running on your local machine, or Eagle machine if you're running it on supercomputer. And then this is the main functionalities that you have within the FABSIM that you're able to use as well. In relation to the VNV patterns in FABSIM3, so the main important aspect was within the VECMA project as well is not to only develop different types of implementation for the UQ analysis, but also try to verify and validate. And what we've done is that we developed 4 different types of VNV within the FABSIM3. So here's some of the examples. So stable intermediate forms, level of refinement, ensemble output validation, and quantity of interest distribution comparison. You can read more about this in link here. Presentations will be also available for your own use. I'm just gonna go forward. To give an example about the multi-scale migration prediction, how it's used for the VVUQ, is that this is the general framework that we applied when we were constructing our migration model. First, you have different types of problems that you would like to select. So for example, I'm focusing on a conflict in Nigeria, and there's people who are fleeing from that to neighboring countries. So I choose a country and the period I want to focus on. Afterwards, I obtain data from public databases that provide me conflict locations where these conflicts happen within the country, geospatial data, and then the total number of refugees within that country. After obtaining all this information, I'm able to construct my model that provides me different aspects that I've gathered in my data selection process. After constructing my model, I'm able to refine it with additional information that I get from other databases or from the reports that are available about this conflict. And then we use Flea code. It's agent-based code that allows us to distribute incoming refugees within a conflict country that are actually fleeing to a neighboring camps. And you're able to run ensemble simulations or sensitivity analysis using this code. Is publicly available. After running our code, we're able to actually get our results and validate it against the data that we have from the UNHCR database. So this is general framework that we applied. So here within this model, what do we have is that we need to verify our model. How do we actually know that our model is true to the reality? Another aspect is we like to validate. So within our framework, we do have validation aspect already, where we achieve our simulation results from the simulation and we compare it to the actual historical data. And then the UQ part is within our input data that we obtain, as well as in our simulation execution. So how our simulation output is impacted by the input parameters that we have, or the key assumptions within our model. And this is a general VECMA migration tube map, where we are able, using the migration application, to integrate with EasyVVUQ and FABSIM3, and we're able to run on a supercomputer using QCG pilot job, or we can actually use FABSIM3 and directly integrate it with the supercomputer. Or there's another option. You can actually use migration application, run different types of simulations, for example, ensembles, replicas within the FABSIM3 and execute it through the QCG pilot job. Another aspect is that I showed you different types of validation and verification patterns. And you're also able to do that within the FABSIM3 by running using the QCG client or QCG broker. QCG client, broker, and QCG pilot job, they are the schedulers that are available. within the Posen supercomputer. So in depth, just to provide more information about how do you actually use the VVUQ for migration, is that the first, of course, you need to install all the softwares. After installing, what you do is you define the space parameters. So you define the input parameters, minimum and maximum values. After which you identify and assess uncertain input distributions. And step 3, your generation of the required samples and runs. Here's a small illustration. I'm inside the FabFLE, the plugin that I mentioned. I'm able to go to the sensitivity analysis. Here I specify my parameters that I would like to investigate. And I also choose only 2 parameters, for instance. I am able to also provide what kind of sampling method I want to use. And also you provide the polynomial order that you like to have within your execution. So just to go again, so parameters, the selection of parameters that you like to investigate only, and then you provide the polynomial order, and then also the sampling method. And then after you execute it in the, you get your results. After getting the aggregation of the output, you analyze and calculate the sensitivity of your input parameters to the simulation output. And also you explore and visualize, update database. If you have any issues or you're not satisfied with the output result that you obtained, you go back and you perform your analysis again. To demonstrate, this is my couple of last slides. In relation to the results, so as I mentioned, we performed VVUQ analysis within migration use case. So as you can see, we've done 2 different types of analysis. First is sensitivity analysis based on dimension reduction, where we use 6 and 7 different types of parameters. And we used polynomial chaos expansion as well as stochastic collocation with polynomial order of 2 and 3. Here you can see the polynomial order of 3. 3 for 7 parameters, and we had more than 16,000 runs. And you're able to see again within the visualization I mentioned, you have the simulation days, and then you have the Sobel indices. And I can see from here that my camp move chance, which is a parameter assumption within my model, has the highest impact. So it's the most influential parameter. If I want to modify it or use different types of ranges, that I can actually do that and then perform another set of analysis. And here what we have is the efficient sampling. So we try to measure uncertainty caused by stochastic model for evolving violent events on the output. So we also worked on different types of propagation of conflict events that can happen in the future. And we try to analyze how this actually affects, and we try to visualize and understand the uncertainty quantification within that. In relation to the validation and verification analysis, what we did perform 2 types of analysis. So first is the level of refinement, where we investigated Sobel indices for each parameter with different polynomial orders, as you can see here on the left-hand side. So we use 3 different parameters, and we try to understand, do they converge over time? And also we've tried to investigate the ensemble output validation. So since our model is agent-based model and stochastic in nature, we run the same model more than 10 times. So this is a fragment of some of the model outputs that we got for our validation. And as you can see, they're all different values, but in the end, it provides the total mean for whole simulation runs that you have. So that's all for my talk. Thank you for your attention.
Thank you very much, Diana. As you know, Peter has had to dash off to an unmovable appointment, but he will be back tomorrow and Thursday. So I will just work with Diana just to field a couple of questions now. And what I'm suggesting is, because we've gone a little bit over our timetable, is that we try and do our sort of discussion Q&A last bit to finish the day.